And we will, first of all, we'll look at the general formula of ethers, the naming, the physical properties, some synthesis, especially the Williamson synthesis, and that will be that. Then we move to the epoxides. So ethers basically have two alkyl groups bonded to an oxygen atom with a bond angle of 112 in the case of diameter eta, and of course 132 in the case of what? Ditet-butyl ether. All that it implies is that in the structure of ethers, the bond angle varies depending on the nature of the ether. And the nature of the ether also varies based on what? The nature of the alkyl groups that are bonded to the oxygen atom. And like I said earlier on, when these ethers are in a ring form, as you can see here, it's a 3-membered ring, a 4-membered ring, a 5-membered ring, a 6-membered ring. Then there are no more ethers, but then they are called epoxides. So when ethers are in a cyclic form, we call them epoxides. And we have the oxirane, which is a 3-membered epoxide. We have the oxetane, which is the 4-membered epoxide. We have the oxolane, which is the 5-membered epoxide. Then we have the oxane, which is the 6-membered epoxide. So if you see an ether, the general formula that you can use to easily characterize them is the R bonding, oxygen bonding R. So you see there's a central oxygen atom that is bonded to two alkyl groups or two area groups. So the alkyl groups or alkyl residues are open chain alkyl residues, or they could also be what? Aromatic groups. That's area groups. Remember, the two R groups can be the same or they can be different. They can be the same or they can be different. If they are the same, that is where we have what we call the symmetrical ethers. What it means that if this R here is the same as this R here, then there could be a form of symmetry. You can cut the ether into two equal halves. So we call those ethers symmetrical ethers. Of course, if the two R's are not the same, they are different, then we call them the unsymmetrical ethers. The oxygen atom in which the two alkyl groups are bonded to is in an sp3 hybridized state. It's in an sp3 hybridized state. Of course, with a bond angle of 109.5 degrees. The same way, the alkyl chains that are also bonded to the oxygen, the carbon atoms are also sp3 hybridized. So that is the general formula of ethers, which is the same as CnH2n plus 1 bonding oxygen bonding CnH2n plus 1. Of course, N can vary for both sides, and that will bring about the unsymmetrical ethers. And when N is the same for both sides, then you have the symmetrical ones. Down here are some examples of ethers. So for the first one down here, you have a methyl group bonded to oxygen and another methyl group. Now, this is an example of a symmetrical ether because the R here, that is CH3, is the same as the R here. So that becomes a symmetrical ether. Assuming over here we had a 1 carbon meter and then maybe a 2 carbon ether here, then the two R's are different, and that would have given us what? The unsymmetrical ether. Here we have the aromatic ether because one of the R, if not the two, is bonded to an aromatic nucleus. So you could have a ring here and another ring here, or one ring and then another alkyl group. But what is important is that because one of the alkyl groups or one of the R groups is an aromatic, we then refer to it as what? An aromatic ether. And over here, when ether is in a ring form, we call it what? Epoxide. So this is an example of a cyclic ether or an epoxide, which we will later look at them in detail. So let's look at the structure and then the shape. Ethers, like water and alcohols, are polar. So an ether is polar because of the oxygen in there. But of course, they are not as polar as water and alcohol. Their level of polarity is minimal and it's not as that in water and alcohols. So looking at the physical properties of ethers, and you are focusing on the boiling point, then we rather will say that the ethers resembles the alkanes more than the alcohols. They resemble the alkanes more than the alcohols in terms of boiling point. And if you recollect, all of you have done Introduction to Organic Chemistry in your first year, Chem 108. And when I was teaching the hydrocarbons, alkanes, alkenes, alkynes, we indicated that the physical properties of the alkanes, and in the case of boiling point, they increase with what? Increasing number of carbons in an open chain. So if you have 2 or 3 alkane chains, which are all straight chains, then the one with more carbons will have the highest boiling point, and then the one with fewer carbons will have the least boiling point. But then we were quick to add that when you start introducing branching, that one introduces another effect on the boiling point of these alkanes. And there we got to know that branching or side chains decreases boiling point. Branching or side chains decreases boiling points. It rather increases melting point. So if you have, let's say 2 compounds, one is octane and octane. There's a noise at the background. At this point, if not that you have a question to ask, please mute yourself. If you don't have a question to ask, mute yourself. And if you have a question to ask, just use the raise hand button, and then you just put up your hand and I'll call you so that we don't distract other people's attention. All right. So in our case, if we are comparing 2 compounds like octane, a straight chain alkane, octane, and then 2-methyl heptane, in terms of boiling point, the octane will have a higher boiling point than 2-methyl heptane, even though they are structural isomers. They might have the same molecular weight or formula. The reason why the 2-methyl heptane will have a lower boiling point is because of the side chain, the branch. Branching tends to decrease boiling point, but rather increases melting point. And so if it were to be melting point, then the 2-methyl heptane will have a higher melting point than the octane. But if it is boiling point, then the octane will have a higher boiling point than 2-methyl heptane. So on the screen, you have some boiling point of diethyl pentane and then 1-butanol. And you realize that the ether boiling point is close to that of the alkane, pentane. Okay, that's why we say the boiling point, the physical properties of what? Ethers resembles that of the alkanes. But in the case of the alcohols, there's a vast difference. Because in alcohol, they are characterized by the presence of what? A hydrogen bond. And hydrogen bondings in alcohols add up to the van der Waals forces. In fact, they are the strongest, and that will require higher energy to break them, hence the corresponding higher boiling points. Now, in the area of solubility in water, that one, the ethers resembles the alcohol more than the alkanes. Remember, water is a polar solvent, and in chemistry, like dissolves like. So water that is a polar solvent would dissolve a polar compound. Now we are saying that alkanes, alkenes, and alkynes, they are non-polar. That is why they are insoluble in water. But then the ethers, because of the oxygen in them, it makes the ethers polar. And so in terms of solubility in water, the ethers are going to be readily soluble. They are going to be readily soluble in water. And so in the solubility context, ethers resembles alcohol more than alkanes, because alcohols are polar. They also dissolve in water. Just that either the ether or the alcohol, which is soluble in water, their solubility decreases when you increase the carbon chain. So let's say you have an alcohol or an ether of 4 carbon, and then another ether or alcohol, another ether. Sorry, if you have an ether of 4 carbons, and an alcohol of also 4 carbons, then again, in terms of the solubility, the alcohol will be more soluble than the ether. But then if you are comparing 2 alcohols or 2 ethers, then as you increase the carbon chain or the alkyl chain of this alcohol or the ethers, then there is a corresponding decrease in their solubility in water. Because increasing the carbon chain, you are increasing the non-polar component of the alcohol or the ether, and that non-polar component is insoluble in water. So eventually, the solubility of the alcohol or the ether will decrease with an increasing carbon chain. Now let's look at these observations. Why alcohols and ethers are soluble in water is because of what? their polarity, because water is a polar solvent. And they are able to form hydrogen bonds. But then, if you look at the alkanes, they cannot form hydrogen bonds because of their non-polarity. And for that matter, they become insoluble in water. Nomenclature of ethers. How do we name ethers? Ethers are considered as alkoxy derivatives of alkanes. Meaning, if you look at the structure of ethers, you can easily add the oxygen to one of the alkyl chain, and that becomes an alkoxy group. Then, when you add oxygen to the other one alkyl chain, the other alkyl chain is seen as what? An alkane. So that's why in their naming, they can be named as what? Alkoxy derivatives of alkanes. So you look at the two alkyl groups, and then in this first instance, the two alkyl groups are the same, 2 carbon, 2 carbon. So any one of them can be your longest chain. And then you consider the alkoxy group, that's the oxygen with the other alkyl group, as a substituent. So when you have a 2 carbon, that one is what? Etoxy. When you have oxygen bonded to a 2 carbon alkyl residue, is what? Etoxy. And if it is 1 carbon, methoxy. If it is 3 carbon with an oxygen, propoxy. If it is 4 carbon, butoxy. So you name the alkoxy as a derivative, as a substituent, and then you add the other alkyl chain as the parent name. So this one will be etoxy ethane. Etoxy ethane. That is correct. And of course, an IUPAC name. The common name is diethyl ether. So for the common name, just look at the two alkyl groups. This is ether, this is ether. So in naming or nomenclature, when a particular group or substituent appears twice, we don't write them separate, ether, ether. We introduce the prefix di. So then it becomes di-ether. Then you add the word ether to it, and that is the common name. Di-ether, ether. If it is a 2 carbon, sorry, if it is 1 carbon on each side, that's a methyl group, then it becomes dimethyl ether. If it's 3 carbon on each side, then it becomes dipropyl ether. But if the carbons chains on each side of the oxygen are not the same, they are different, like this one. One is 2 and this one is 1 carbon. Then automatically the longer chain, the longer residue is considered the alkane name or the parent name. Then the smaller one forms the alkoxy group. And so it becomes methoxy ethane. Methoxy ethane for the IUPAC name. But when it comes to the common name, the two alkyl groups are mentioned separately because they are different. This one is ethyl and this one is methyl. Now, ethyl and methyl, if you are to arrange them in alphabetical order, E comes before F. So the same way you are giving the common name of ethers and then the alkyl groups are different, you go by that same strategy. So the ether is written first, followed by the methyl, then you add the word what? Ether. Over here, you have 2 carbons here and 3 carbons here with the chlorine on it. So the 3 carbons with chlorine is your longest chain. So that probably will be the parent name. Then the 2 carbon side chain will add to the oxygen and then be called etoxy. But then because the longest chain, the 3 carbons has a chlorine on it, then it's advisable that we do number the chain by way of giving the least number to the chlorine. So you start from here, 1, 2, 3. In that case, the ethoxy is on the third carbon, and then chlorine is just one carbon. And so the name becomes 1-chloro, 3-ethoxy propane. So ethers generally may be symmetrical or asymmetric. And whether it is symmetric or asymmetric, these are the rules governing their names. Any question? Any question? All right. Yes.
Doc, please, can we have more nomenclature so we can name them?
All right. Then let me use my chem draw to help you get more structures for us to try our hands on to be sure that we are on the same page. So let me.
And sir,
Yes.
please kindly us through the naming again. We'll be glad if you go over the naming again.
Yeah, so going over again probably might be me using other examples. And I keep on saying the more examples, the better the understanding will come. So let me use a chem draw and then see if I can draw more structures for you to. All right, so look at this ether. How you can all see?
Yes, Doc.
All right.
Yes, please.
So it's an ether because you can, and this is an unsymmetric ether. Apart from the two alkyl groups bonding to the oxygen are not the same. This side has 3 carbons, 1, 2, 3, and this one has what? 1 carbon. So it's an unsymmetric ether. But what we are saying is that if you are naming this ether, that's the IUPAC name. Look at the 2 alkyl groups. Which one is the longest? The 3 or the 1? Which one is the longest?
The 3.
The 3. So the 3 is considered as what? The alkane name. How do we name a 3-carbon alkane? Propane, isn't it?
Yes, sir.
So then that becomes the parent name, propane. Then you consider this one, you consider the oxygen, okay, the oxygen to be part of the short carbon or the short chain. And that is what we call a carboxy group. And the carboxy group, if it's a 1 carbon from methane, it's what? Methoxy. If it's a 2 carbon from methane, becomes what? Ethoxy. If it's a 3 carbon from propane, becomes what? Propoxy. This one is what? A 1 carbon, so methoxy. So you start the alkoxy as the substituent, and you mention methoxy. And then you add the parent name, a 3 carbon alkane is what? Propane. So it becomes methoxy propane. It becomes methoxy propane. Please, is this one okay?
Yes,
This is
Doctor.
Correct.
Yes, please.
All right. I'm going to give you more examples, Now, you see, from this name, we said methoxypropane, but then they've indicated 1-methoxy. So we are just trying to say that longest chain, the 3 carbon, if you number it from the functional group, then it goes to be from here, 1, 2, 3. So it means that the methoxy group is on the first carbon. So you say what? Methoxypropane. Please, is that right?
Yes, sir.
No. Come
Well,
again, sir.
hold on. I will help you out. Let me give another example so that you appreciate why the position is 1 and it should be part of the name.
Yes, sir. Yeah, from the same example, can you also say propameta ether?
That is the common name, but hold on, okay? I want us to appreciate the IUPAC names first. All right, please. The first structure and then the second one, are they the same?
No.
No, doctor.
No.
Here you can see that this side of the alkyl group is 2 carbon and this one is 1. But from here it is 3 and 1. So if you want to name this one, then the 2 carbon is your longest chain. So the continuous, the longest chain is 2, which is what? Ethane. Then the 1 carbon chain add the oxygen to it and you call it methoxy. So it becomes what? Methoxyethane. Methoxyethane. Now let me generate that name for you first. Then I'll compare the two and then so you see we have methoxyethane there. The question is, why is it that the first one we indicated 1 methoxypropane, but the second one, if you are to also number the longest chain, it will start from here 1, 2. So it means that the methoxy group is on the first position. So why didn't we say 1-methoxyethane? But then we just ignore the position. But for this one, it's important we bring it. Can somebody tell me?
Hello, Doc.
Yes.
Doc. Okay.
Yes, go ahead.
Doc, please, I'm trying. Okay, I think that when we change the position of the ether, the name will not change because when we bring it to the let me label it. So when you label it from 1 to when you change it to the other side, the name will not change. Like when you bring the oxygen to the other point.
Yeah.
Yes.
When you bring it to this point, what will happen?
No, I'm talking about the second one, the second drawing.
Okay. When you bring it to here,
Yes,
it will still be the same thing,
yes,
methoxyethane.
please. But for the first one, when you change the position of the oxygen, the name will change.
Okay, I think that is a good reason. That's a very good reason. Yes. In fact, all that I want to add to what she said is that now the methoxy group, which you are considering as a substituent, okay, this group, is that right?
Yes, doctor.
When you look at the first one, if we pick it from there, you see it is on the carbon 1. If we pick it from here and then we bring it here, that is the carbon 2. You are going to get this particular structure up here that I have drawn. Okay. But would this name be the same as 1-methoxypropane? propane, and the answer is no. Because now the position of the methoxy is no more on the 1, it is on the number 2, it's on the second carbon of the long chain. The long chain still remains 3. Your longest chain is still what? 1, 2, 3. Just that for the first one, the methoxy group was on carbon 1. For this second one, the methoxy group is being positioned on the second carbon. So this is 1 methoxy propane, and this is 2 methoxy propane. They are isomers, structural isomers. They differ in their structure, but they are not the same. That's how come the names are different. So in the case of the first one, the reason why we brought the 1 is because there is another way that you can change the position of the methoxy group, and that will give you a different compound. And so when that is the case, then it is important that you indicate the position to be able to distinguish between the two. But for this one, like she said, if you pick this methoxy group from here, which is on carbon 1, okay, and then you pick it from this carbon and you bring it to this other carbon, it will still be the same carbon 1. So whichever position you put the methoxy, whether it is this carbon highlighted or it is this carbon, it's still going to be what? 1. And that is why it is not important to bring the position 1 and make it methoxyethane. But for this 3 carbon, there are other ways that you can position the methoxy, and that will give it a different name. And that's what I've shown up here. And so that's why it is important that you bring the position 1. And so if in an exams, this first one, you write methoxypropane without bringing the position 1, it is wrong, because there's another way that you can also locate the methoxy, and that will give it a different name. So here, the position is very, very important. Let's see other examples.
Say,
Yes.
say, please, the third one, that one, down there, is it not branching? So if you count it continuously, 1, 2,
1,
2,
2, 3. Okay. When you say continuous carbon chain, the carbons are connected. So this is 1. Okay. And this is 2.
Okay.
And this is 3.
Okay.
And you can count from down here too, and this is 1, this is 2, and this is 3. So it is 3 propane. But then if you are doing the counting, whether from left to right or right to left, when you get to the second carbon, that is where the methoxy group is positioned. So you have to give that position number 2 to the methoxy, and becomes 2 methoxy. Over here is a straight chain. So when you're counting from here, you can count from here 1, 2, 3, and that is 1 methoxypropane. You can also count from here 1, 2, 3, and that will be 3 methoxypropane. But we all know that when you are counting, when we're dealing with alkanes, when you are selected your longest chain and you are numbering the position of the substituent, we always go for the least. Okay, we number in such a way that we get the least position, and that's why you cannot start from here to make it what 3 methoxypropane, but you have to start from here so that you make it what 1 methoxypropane. All right, let me try and come with another structure.
Hello, sir.
Yes.
Please, does that mean that after getting your longest chain, every other chain is treated as a substituent?
Yes. And in the case of ethers,
Okay.
in the case of ethers, first of all, when you take your longest chain, the other chain becomes your substituent, okay, a carboxy substituent. But I was going to give you another one in which beyond the carboxy substituent, there will be other substituents as well. And when you have a situation like that, how do you go about it? So let me show you that one. Please, have you seen this one? Have you seen this? Can you see?
Yes, sir.
Yes,
Good.
doctor.
So now, what are the alkyl groups here? The alkyl groups here are this one.
Yes,
How many
please.
carbons are there? 2. Okay. 2 carbons. If you take the longest, it's 2 carbons, isn't it? Then over here, we can have 1, 2, 3. Okay, which is also longer than the 2. Then we could also have 1, 2, 3, and 4, which is also longer than the 3. So it means that for this side of the alkyl group, we can have 1, 2, 3, and then 1, 2, 3, 4. But we know 4 is longer than 3. So we will prefer the 1, 2, 3, 4. So that this one over here becomes a substituent on the longest chain. So now you see we are looking at 2 different substituents. The methyl substituent on the longest chain and then the alkoxy substituent. Okay, so there are 2 different substituents here. But what is important is that your longest chain is 4, and 4 is what? Butane.
Butane.
Then the alkoxy group is what? 2 carbons. So that one is what? Ethoxy. And then this methyl group here is what? Methyl is 1 carbon. But you need to number the longest chain so that you know the position of what? This particular methyl group. And you always have to number from where the alkoxy will be given the least number, the alkoxy substituent. So you definitely will number from here. So you are going to have 1, 2. So the methyl group here is on the second carbon, 3, and 4. So that will be your numbering system. Sometimes when you are drawing, you also have to write it down and then try to follow up so that you can appreciate it better. Now, what is the name? The name is 1-ethoxy 2-methyl-butane. 1-ethoxy because the longest chain is 4. 1, 2, 3, 4. So that's the butane. Now the ethoxy alkoxy group, if you are numbering the longest chain, you start from here. So 1, 2, 3, 4. So the ethoxy is on the first carbon. That's why it says what? 1-ethoxy. Then the longest chain, which is butane, also has a substituent methyl group, which is on the second carbon. So you have 2-methyl-butane. So the question that is important for you to note here is the alkoxy, the alkoxy substituent, and then the substituent on the long chain, which one should come first? And it's always the alkoxy substituent that's its name first, before any other substituent that is on the long chain. Sometimes when I'm explaining, get the understanding first before you even ask a question. But if I'm explaining for understanding and then you are interrupting, what it means is that no matter what I'm explaining, you will not understand. Anyway, any question? Yes.
Sir, my problem is the 1.
You see?
I didn't understand
it
the
is
1.
a problem because whilst I was explaining, you were interrupting. You just have to understand. What I'm saying is that look at the oxygen, and there are 2 alkyl groups. This one, how many carbons are there?
So 2.
Good. Then look at the other side. Okay, that is this alkyl group here. Okay. Now this one, there are 2 chains there. So I want to point out the 2 chains. You have 1 here. We have 2 here. And then we have 3 here. Then you can also have 1 here, 2 here, 3 here, and then 4 here. So there are 2 different chains. One is 3 carbon, one is 4. So we go for the 4. For 4 is longer than 3. Now, when you go for the 4, it means that this particular 1 carbon chain, methyl group, is also a substituent on the longest chain of 4 carbon. So the one that I have circled, that methyl group, is a substituent. And we know substituent must be named before the parent name, and their position must also be indicated. Then the oxygen with the longest chain, that's the alkoxy group, is also a substituent. Okay, so what it means is that now we have to number the longest chain. And if you are numbering, the focus should be on the alkoxy here, where it is positioned. Okay, that one should be given the least number. So if you go and start numbering from this side, 1 here, 2 here, 3 here, then the meter will be 3. Then 4 here, then the alkoxy group here, that's with the oxygen, is on the 4th carbon. But when we start numbering from here, 1, 2, 3, and then 4, then it means the alkoxy group here is on the 1st carbon. And that is why the ethoxy is what? Position 1 ethoxy. And then the methyl is what? 2. But assuming you have not started numbering from here, this carbon, and then you had started numbering from here, then the alkoxy group here will be 4. Position will be 4. And the methyl group here, position will be what? 3. But you see, 1 and 2, and then 3 and 4. Which one is the least? This basic rule of IUPAC, that anytime you are numbering to give positions to substituent, go the direction that you always will have the least number. So in this case, we will number from right to left so that the alkoxy will be 1, the meter will be 2. Instead of numbering from left to right, for the alkoxy to be 4 and then the meter to be 3, which will give us high numbers for the positions. Is that okay?
Yes, sir.
All right. Are we to move on, or you need more examples?
So give us one more, then we continue, please.
All right. So let me give you one more example. All right, can we try this one? I want you to try yourself, and then I'll come in as well. So try and see if you can name it. Yes, who is ready?
Sir, I want to try.
All right, go ahead.
So 4 meter oxy, 3 methyl heptane.
Please come again.
Sir, 4 meter oxy, 3 methyl heptane.
Okay, Lucy. Or is it
Sir,
Lucky?
please, I want to try to.
Yes, go
Yes,
ahead.
sir.
Mercy.
Okay,
Four.
so I had
Okay.
3-methoxy, 4-methyl-heptane.
3-methoxy, 4-methyl-heptane. Where did you
So,
come
sir,
from?
I
Is it
have
from here? 1, 2, 3, 4. 1, 2, 3, 4. Whichever direction you are going, the methoxy is on the 4th carbon.
Yes, doctor.
Yes, Harriet.
Doctor,
I
please,
have
I got
4.
4-ethoxy, 3-methyl-heptane.
4 what? Ethoxy or 4-methoxy?
4-ethoxy.
Ethoxy.
Yes,
No.
4 methoxy, 3 methyl-heptane.
The short carbon chain, this one, which is bonding to the oxygen. Is it methoxy or ethoxy?
It's
Methoxy.
methoxy.
It's
It's
methoxy. It has only one carbon.
Oh,
It has
okay.
only one carbon.
I thought because the lines are 2, no. Okay.
No,
All right.
the line represents a bond. Okay, the line represents a bond. The end of the line is what? A carbon. So
Thank you
this
very much, sir.
so this particular line, this side here is a carbon, and then this line is a bond, and it's bonded to what? Oxygen. So take note of that.
Thank you very much, sir.
Welcome. Any other person? Emmanuel Santi, your hand is up.
Hello, Doc. I
Yes.
had 4-methoxy, 5-methyl-heptane.
No, it
Okay,
won't be
so
five, it will be 3.
Asante, your challenge is that whichever direction you number from, the methoxy will be 4. Okay, so whether it's from right to left or left to right, you are getting 4.
Okay.
So now your
Okay.
concentration should be your concentration should be on the methyl
Okay.
group. If you go this way, that's where it becomes 5. If you go this way, that's where it becomes 3. And we prefer the 3. Yes, so take notes.
Okay.
Good.
Okay, please. Thank you.
You had
Doc,
what?
thank you.
Yes, somebody was saying something.
Yeah, my methoxy was on the 3rd carbon.
Yours was on the 3rd carbon.
Yes, please.
Did you count from where? Where did you count from? Here?
I counted from the top one.
Oh, okay. You counted from here.
Yes, please.
But if you count from here,
So
1, 2, 3, 4, 5, 6, you don't get the longest chain. That is 6. But when you count from here to here, it is 7. And we say that you choose the longest one, like the previous one I gave you here. You know, we didn't count from here because if you count from here, it's giving you 1, 2, 3 carbons. But if you count from here, it's giving you 1, 2, 3, 4. You get it? All right.
Hey, Doc.
Yes.
I was comparing the one that we did before this one. You see, this one, the lines after the ether is 2.
Okay. Yes.
Okay. So that's why I got
pay attention. This one is what we call the bond line method. This how to draw this organic structures. It's called the bond line method. And this is what I will use in your exams. I prefer using this one than the one you write carbon with hydrogen and all those things. Okay. Life is short and it is easier to draw this one. So I won't waste time to go and use the carbon hydrogen and then spend about 1 minute on one structure. Whilst this one, I can use 30 seconds to draw as many. Life is short. So yes, life, that's what I'm saying. Life is short. So you don't have to waste more time. Okay.
Yes.
So
yes.
I'll be
you don't have to stress yourself. All right. Thank you.
So I think you are doing well with the naming of ethers, but then let me see if I'm to modify. So now let me just check something. Have you seen the name?
Okay.
So you see, it's the same thing you got.
Yes, doctor. Yes,
Good.
yes, yes.
Now let me modify that particular structure a bit, and let me see whether you will be okay with it. Now check the new name. You see, now that there's another substituent, a meter also here, but that one is closer to this end. If you number from here, this one is 2, and this one is what, 5. But if you number from here, this one is 3, and this one will be what, 6.
So with this, you know,
And then the
how
methoxy
do you prepare them?
is a
How do you prepare them?
is the person talking to me?
Oh no.
Richard Appiah. Divided attention. Minus 10. Whenever your exams papers get to me, I will take 10 marks. All right.
He has failed already.
Yes, he should prepare for restate.
So, Mr. Samanoye.
Hello, please. So now that is that. But then let me modify again. Instead of the 2 metal groups, now let me change one to a halogen. So let me make it bromine. What is the name? Five bromo.
4 methoxy, 2 methyl heptane.
Now there's something that you should watch here. You see that before I introduce an inorganic substituent, always the methoxy or the alkoxy comes before the other substituent, ACAB substituent. But for inorganic, they should even come before the methoxy. Please, is it clear?
Yes,
is it clear?
Yes, sir.
Just look at this one. Just look at the name here. You see that the one ethoxy was written before the 2 meter. And then the other examples we gave. But as soon as I introduce a halogen, inorganic substituent, for those ones, they should always come before. They should always come before the methoxy.
Oh, okay, doctor. Then let's name it and see.
The name is already there. Okay, let me bring it back. As soon as I bring the bromine, okay, and I click on it, now you see that the name is there.
Sir.
Yes.
Sir, please. When you are naming them organic and inorganic substituents, meaning that the organic one they have a higher priority in terms of position than the inorganic one.
Okay, so now that one, don't be quick to make that statement. Now, what you have to do is that the bromine is 5 here. So what you need to do is, if you number from this side, let me use this one. If you number from this side, okay, as 1 here, the bromine will be what? 3, isn't it?
Yeah.
And then the methoxy will be 4.
Yes, sir.
And then the meter here will be what? 6.
Yeah.
So now you have what? 3 and then what? 6. That's the position of the 2 substituents. The bromo will be 3. The meter will be what? 6.
6.
3 and 6. When you add them, it is what? 9, isn't it?
Yes, it is.
Yes, sir.
Now, when you start from here, the meter will be 2. The bromine will be what? 5.
5.
So 2 and 5. When you add them, it is what? 7.
7. Okay.
So the sum of the positions, which one is the least? It is the 7.
Oh, okay, sir.
So here we are not giving priority to the organic substituent, but we are considering the Ayupa rule that says that we should go for the position that will give the least numbers to the substituent.
Oh, okay, sir. Understand.
Great.
Well understood. Okay, thank you, sir.
Great. Yes. Is there a hand up, Harriet?
Oh, sir, please, it's an old hand.
All right. Yeah, your hand is up. Yes.
Yes, sir. You know, in naming, we have to take into consideration the alphabetical addition. What if the inorganic component, the alphabet is maybe start with P or Z? How then would you name it? Which comes first before the organic?
The rule is that we have organic and the inorganic substituent. Okay, always the inorganic should be written first before the organic. But then when you have 2 inorganic, and I'm going to give you another example. When you have 2 organic, then you arrange them in alphabetical order. And when you have 2 inorganic, you also arrange them in what? Alphabetical order. So let me introduce other substituents. So now let me bring a second inorganic group, which is, let's say, chlorine. Okay. And then let me bring, let me lengthen the chain from 7 to 8. And let me increase this one. And let me bring another group here. Please, can you all see this new structure?
Yes, sir.
Yes, sir. I'll bring this one. I'll bring this one in your quiz.
Yeah.
In your quiz 1.
Oh.
But then it's a multiple choice. So I'll bring the various options for you to choose from. Now, what we are saying is that if you take the longest chain, can somebody tell me the longest chain?
8.
8. 8. So
Yes,
we have 1, 2,
8.
3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6, 7, 8. So 8. If it is 8, then as for the methoxy here, okay, you now have to check. 1, if you number from left, you have 1 here, 2, 3, and then it is 4 here. But if you number from here, 1, 2, 3, 4, and it is 5. So at this stage, don't bother yourself with the substituents. Only consider the alkoxy substituent. This one. That should be your focus here. The previous one, whichever direction you were going, was 4, 4, 4. But now, after me extending the chain, if you move from left to right, it is now on the 4th position. But from right here to left, it is what? On the 5th position. So 4 and 5, we prefer what? 4. I hope that is clear.
Yes, doctor.
Yes. No.
So you number from here. 1. So this group is a metal group. The down one here. And it is on the 2nd carbon. So it will be 2 metal. Then this bromine is a substituent on the 3rd carbon. So 3 bromo. Then this chlorine is on the 5th carbon. So 5 chloro. Then this ethyl group is on the 6th carbon. So 6 ethyl. So all the substituents, now you know their positions. But then we have 2 of the organic substituents, ethyl and then methyl. So in arrangement, E comes before what? M. So the 6 ethyl will come before the 2 methyl. sequence. The bromo and then the chloro. You also arrange them in what? Alphabetical order. The 3 bromo will come before the 5 chloro because B comes before C. And so with this, somebody should be able to tell me the name.
3 bromo.
Okay.
5 chloro.
Relax. We are all learning. You are giving the names to your colleagues for them to follow and know that they are also understanding it. So take your time and give the name, please.
3 bromo. 5 chloro. 6 ethyl. 4 C. 2 methyl octane.
No. Okay, sir. We have the
3 bromo. 5.
I think he almost got it. He almost
3 bromo.
Yes, somebody should also come in.
So I want to try.
Yes, go ahead.
So it is 3 bromo, 5 chloro, 6 methyl, 2 methyl, 4 methyl oxy octane.
Okay, sir.
Hey.
Okay, sir. I have the name to be 3 bromo.
Let me try.
Oh, let's one at a time, please. One at a time. Yes.
3 bromo, 5 chloro, 4 methoxy, 6 ethyl, 2 methyl octane.
Yes. Okay, people are saying yes. So let's see whether that is it.
I disagree.
Yes, that is it. Is that what he said?
No, that was what I said, sir.
That's what I said.
Yes, sir. That's what he said.
All right. So please, all that I'm saying that I am quiet. Just draw this structure and then get the name there, and then let's continue. I won't say anything again.
Don't confirm for us, sir.
When you are done, let me know.
Don't confirm.
Sir?
Hey, doctor.
Today, my good friend Festus have not spoken. Maybe he's understanding things well. Or he's
Oh, sir, I've spoken.
Yeah.
Oh, okay.
I'm with you. I mean,
You are with us, eh?
But it is. I'm with you.
Oh, okay, all right.
Hey, doctor. This your drawing.
It's not drawing, you. This is not visual art. This is chemistry. They are structures. They are compounds.
Hey.
So we are not doing visual art here.
Yes, one way that's a final papa is already young.
Please, Wisdom, your hand is up. Do you have a question? Or is an old hand?
Hello, Doc.
Yes. Ebenezer, go ahead.
Okay, so with the last structure, I thought the ethyl will come after the methoxy for us to have 3 bromo, 5 chloro, 4 methoxy, 6 ethyl, 2 methyl octane.
So you see the previous examples I gave. Let me go back and then see. Maybe let me get something down here. Let's see something. Maybe that will settle. I hope you can see the structure.
Yes, sir.
All right. Just a minute. Those of you who want to get yourself abreast with the use of the chem draw, I'll see. I can share with you the program so that you can install it on your laptop, and then you can even use it to learn from alkanes, alkynes, alcohols, and all the functional group chemistry. When it gets to the nomenclature, every structure you draw it, and then it can help you with the naming. And then when you are teaching to
Thank you, sir. When you are done, you send it.
okay, so this one is 2-ethoxy, 3-etapentane, but that is not what I wanted to achieve. Let me modify it to see. Let me take the meter from here and then bring it here. No. Okay, I think this one should be able to help. So what I wanted to say is that you see, with this one, the alkoxy group came before the ether and then the meter. All right. This is because the alkoxy group is E, and then this ether is also what? E. Is that right? So because they all start with EE, then we give priority to what? The alkoxy group. Now the name that is down here, you see that the alkoxy group is what? It's M, methoxy. But then this ether here is what? E. And E will always come before M. That is why this time around, we gave the priority to the ether before the methoxy. Let's go back to this. If I change the ethoxy to methoxy, so let me clean one of the carbon chains. Now, you have 4-ether now coming before the 1-methoxy. Simply because the E alphabetically comes before M. But where they are all of the same alphabetical letters, EE, then the methoxy must come before the ether. Please, is that clear?
Okay, sir. Sir, it's clear now.
Good. Good.
Yes, Doc.
So now I think we spend more time here. Let me move on. All right. Please, can you see the slide?
Yes, sir, we can see it.
Yes,
All
sir.
right. So one thing I want you to know is that it is not always that I will draw the structures and then ask you to name it. Sometimes you can be given the name and then you'll be asked to draw the structure. So an example is what you see there. Write structural formulas for each of the following. That as a proper ether, ether, phenyl ether, 2-ethoxy ethanol. So you can also be given the names to draw the structures. Okay. So take note of that. Now, how do we prepare ethers? The first one is the acid catalyzed condensation of alcohols. When you have two alcohols, you can condense them and form an ether. Now, this particular method can only be used for symmetrical ethers. That is ethers that have the same carbon, alkyl group. So please take note of that. Please, a minute and let me pick this call.
So please, can you go back so that I can capture that one?
He said a minute is answering a call, so when he comes, then you ask him.
Okay.
Oh, he is in the slides that he gave us now.
All right.
Yeah, it's the same thing that he's reading.
Hey, your man slice.
Oh, it has been given to us long time, even before he started last week.
Wow.
Is it Alex?
You can
Watch
contact
your slide. Right, is it Alex? You said the slide.
Abraham. Abraham.
Yeah, Asantua.
Be serious. Be serious.
Oh,
Be serious.
I don't have the slide. I don't have it.
Abraham, please, here
I
too.
placed it in the group.
Asanto, don't mind him, he has it.
Asantua, share for us to get, okay? I think it's
Yeah, please,
all.
we say it. Ordain head teacher.
Okay.
Is it lecture
Okay.
by lecture? All of it.
Am I the only person who is not hearing anything or everyone?
Oh, he said
Doctor
he's
said
busy,
he's
so he
doing
will attend
something
to us later.
and he will come back.
Okay.
Yeah.
I thought maybe.
Yeah. I see you. Where is Sammy?
I thought maybe
Where are my people?
I'm in space while you are on
David,
Earth.
you are still on net.
Okay.
Please, I think it's being recorded.
Yeah.
It's being recorded, though, please.
Yes, please, sorry for the break. There was an emergency I had to attend to. So I think we can continue. All right, so I was talking about the first method, which is the acid catalyzed condensation of alcohols. And I was saying that this method actually is used to prepare only symmetrical ethers. That is ethers that will have the same alkyl chain on both sides of the oxygen. So you only need 2 moles of the alcohol. And if the alcohol has 1, 2, 3, 4 carbons, then it means that both sides of the oxygen will have what? 4 carbons. If the alcohol has 2 carbons, then both sides of the oxygen will have 2 carbons chain. So this is one of the methods, but then it is only used to prepare symmetrical ethers. If you want to prepare an ether where the 2 R groups are different, then you cannot use this acid catalyzed condensation of alcohol as a method. The second method is the Williamson ether synthesis, and this route can be used for both symmetrical and then unsymmetrical ethers. It can be used for both symmetrical and then unsymmetrical ethers. It involves an SN2 reaction of a sodium alkoxide with an alkyl halide. It can also be an alkyl sulfonate or an alkyl sulfate. So if I have an, let's say, sodium alkoxide group here, and then I have an alkyl halide, remember the reactivity of alkyl halides. The halogens are partially negative, while the alkyl groups are partially positive. So if that's the case, then you expect the negative end here of the alkoxide to bond to the positive end of the alkyl halide, and that will break off. So whatever the R that is on the alkoxy, the oxygen is bonded to another R group from the alkyl halide, and that will give you your ether. So if the alkyl chain on the alkyl halide is different from the R on the alkoxy, then you form an unsymmetric ether. If it is the same number of carbons, then you form the symmetrical what? Ether. So the Williamson ether synthesis is most successful when the alkyl halide is one that is reactive towards SN2 reactions. Remember, methyl halides and primary alkyl halides are the best substrates. So we are saying that in the Williamson ether synthesis, the type of alkyl halide also counts in the yield of the ether that you are forming. Okay, if it's a methyl alkyl halide or a primary alkyl halide, then the reaction gives you good products. The secondary and the tertiary alkyl halides are not suitable for the Williamson ether synthesis because they turn up to go through what we call E2 elimination rather than the SN2 substitution. So ether Williamson synthesis is an SN2 substitution, but when you use an alkyl halide, which is a tertiary or a secondary, it ends up that there will be some side product or side reaction via E2 elimination. And so some of the product that you form will become alkenes. You form alkenes rather than what? Ethers. So that is also the limitation for the Williamson ether synthesis. So over here are some equations. When you have a cyclohexanol, and then you have your sodium in ethoxy, then you form, so it's the alkyl component here, the CH2CH3, okay, that is coming to bond with the oxygen over here, and then you form that. There's an alcohol group here, which is a secondary alcohol. So when you add your sodium hydride, which is a base, and then your primary alkyl halide, then the CH3 from the alkyl halide will replace the hydrogen and form your ether. Now, if the alkyl halide is to go, or the halogen is to go to maybe a secondary or a tertiary, then that one to be difficult for you to form the ether products. So these are some questions. I will share. Have I shared this slide with you, please? Have I already shared them with you?
Yes, doctor.
Yes, please, you have it.
Okay, you have them. Good. So please, those who don't have it, get them. Okay. And then there are some questions, and then this is that you need to know, and then revise with it. So these are all examples following the SN2 reactions. So far as you have the understanding that you will need a methyl or a primary alkyl halide reacting with an alkoxide group, you form your ethers straight away. All right, so let's look at the reactions of ethers. And here, ethers are very unreactive with many reagents, and that is why most of the time we use ethers as a solvent, organic solvent, in the chemistry lab. Because if you are extracting organic solvent and then it's able to react with the solvent that you are using for extraction, then it can change to something else. So mostly because ethers like dimethyl ether, diethyl ether, they are non-reactive, they can be used, as solvents for most extraction processes. So the low level of reactivity, along with the ability to dissolve non-polar substances, makes ethers so often used as solvents when carrying out organic reactions. So take note of this point very well. It's very important. Because of the low reactivity of ethers, and also because of the ability to dissolve non-polar substance, it makes them used as what solvent whenever we are carrying out organic reactions or extraction processes. And also most of them are volatile, inflammable. So you should take note of that. Now, acid catalyzed cleavage. You can cleave an ether in the presence of an acid to form an alkyl halide. So if you have so when you heat the alkyl ethers with a strong acid, and here we are referring to the halogen acids, HI, HBr, sulfuric acid, hydrochloric acid. All this strong acid can cause this dialkyl ethers for the carbon-oxygen bond to break. So what is happening is that the acid as a catalyst will cause a breakage here. The oxygen carbon bond here will break. So it's a 2-carbon chain. Then this side will also break. Also a 2-carbon chain. And they all will form a 2-carbon alkyl halide. And then water is evolved as a byproduct. So that is one of the reactions of what? Ethers. In the presence of an acid, you can produce alkyl halides from them. So that is the mechanism. I will not ask you for the mechanism, but the mechanism is just there for you to appreciate how the alkyl halides are formed from the acid catalyzed reaction. These are more examples. Then you have oxidation of ethers. So when you have ethers and you oxidize them, you form what we call the hydroperoxide and the dialkyl peroxide. So oxidation of ethers leads to the formation of hydroperoxide and dialkyl peroxide. Then these ones are epoxide, so I don't think I will touch on them here. So that is that on the ethers. And so we move to the epoxides. Do we take a break or we continue?
So let's hit 2
Dog,
p.m. and then take a break.
Yes, let's
For a break,
continue.
let's hit 2 p.m.
All right. So now we start with the epoxides. So we say the epoxides are also ethers, but then they are cyclic ethers. So if you see an eta functional group like this, the alkyl groups are this. And then for the epoxides, they form a ring. And it can be a 3-membered ring, a 4-membered ring, a 5-membered ring, and so on and so forth. So epoxides are cyclic ethers with 3-membered rings. And of course, the 3-membered rings is what we call the epoxide. And then another name too is what? The oxy ring. So when you see a 3-membered epoxide, it is the same as what? Oxy ring. Then the common
Doc,
name
please,
is the,
what do you mean by 3-membered rings? The
okay,
rings are
so
made up of only 3 or what?
the ring size are 3. So if you take what you see here, okay, you see it has 2 carbons and then 1 oxygen, but then the ring has 3 sides. It's like a triangle, so it's a 3-membered ring. If it's like a square, it's like a 4-membered ring. Okay, so I'm talking about the ring size. So a 3-membered ring, epoxides are called the oxy rings, and their common names are ethylene oxide, apparently because they are formed from some corresponding ethylene alkenes. Now, we need to know how to name epoxides. So kindly, before we go to the synthesis, kindly let us look at the naming, okay, using the chem draw. All right. So if you can see my screen, these are 3-membered, 4-membered, 5-membered, 6-membered epoxides, and these are their names. But then the 6-membered ring can also be called oxane. Oxane. So where we have this one, it is also called what? Oxane. It's also oxane. That's the tetrahydro 2H paran. And then this one is also called the tetrahydrofuran, or the THF. And the THF2, you can as well call it the oxacyclopentane. Oxacyclopentane. So that's also another name. But our focus is going to be on the oxyring, okay? It's going to be on the oxyring. That is a 3-membered ring. And over there are 2 ways that we can name it. So I'm going to get some examples, and then we name them. So let me just have some examples here. All right. So this one, the name is 2-ethyl 3-methyl oxyring. Remember this type of naming, and when in an exams you are asked to name it, you can choose the one that you are comfortable with, okay? This one is the oxyring method. So we know that the 3-membered ring here is what? Oxyring. So any group on it is a substituent. So if you are giving this name, you consider this one as oxyring, that is the backbone, of which you have what? A 2-membered 2-carbon chain on it, which is ethyl, and then a 1-carbon chain, which is methyl on it. Now, when you want to know the positions of when you want to know the positions of the substituent, you start counting from the oxygen. Okay, you start counting from the oxygen. So the oxygen is 1. Then you come to this carbon where the ethyl is 2. Then you come to where the methyl is 3. You can also count from here oxygen 1, where the methyl is 2, and where the ethyl is 3. The reason why we prefer this one, the ethyl being given 2 and then the methyl 3, instead of the methyl 2 and then the ethyl 3, is that in writing them, E comes before M. So for that reason, we need to give the ethyl the least number. And that's why we counted in a clockwise direction, so that the ethyl will be 2 and then the methyl will be 3. Simply because in writing the names, E comes before what? M. So you have 2-ethyl 3-methyl oxyring. So that is that. Now let's take another example. Let me modify this. Still on the oxyring method. Okay. So now with this one, you see I've introduced another carbon in the chain. And the name is, so over here is what? Isopropyl group, okay? Isopropyl group. and this is meter. So 2 isopropyl 3 meter oxygen. You can continue to modify it and then it will give you different names. Now let me go this way. And then this whole group is seen as what? A secondary butyl. So you have what? 2 secondary butyl 3 meter oxygen. Now, when you go this way, you're having 2 meter 3 pentan 2I oxygen. What it means is that now this substituent is a 5-membered ring. 1, 2, 3, 4, 5. So it starts with what? Pentyl, and P and M comes before what? P. So for the first time, if you number the oxygen 1, you have to come to the meter as 2, and this one as 3. Okay. Then you realize that the metal is directly bonded to the oxygen. But then the 5-membered ring here, okay, it is though on the 3rd carbon to the oxygen nucleus. This carbon here, the point of attachment is 2, because you are numbering from here 1, 2, 3, 4, 5. So that's why we have the pentan 2R. So it means that it's like a substituent on another substituent. So that is also another way to name oxygen. The truth is that the oxygen nomenclature is used for simple structures, simple epoxides. As soon as you make the complex, you make the structure complex, then it will be difficult for you to now use the oxygen nomenclature. But for simple ones, you can always use the oxygen to name them. So for complex epoxides, we have to adopt a new name. So this one is 2,3-diethyl-oxygen, and so on and so forth. Now, the other method for naming is this. What you do is that consider the epoxide group as on a particular long chain alkane. So over there, you consider this carbon 1, 2, 3, 4, 5, so that it's like a hydrocarbon, a 5-carbon chain, which has the epoxy functional group on it. So you number the long chain so that you give the least position to the epoxy functional group. Now, if you number from down here, this carbon with the epoxy group will be 2, and this one will be what? 3. So the name then becomes 2,3 epoxy. So you just indicate 2,3 epoxy, and then the longest chain is what? 1, 2, 3, 4, 5, and 5 is what? Pentane. 2,3 epoxy pentane. 2,3 epoxy pentane. So when you come here, this particular one, the longest carbon chain is 1, 2, 3, 4, 5, 6. So that is what? Hexane. Then you number 1, 2, 3, 4. So it will be 3, 4. If you number from here, 1, 2, 3, 4, 3, 4. For the first one, if you number from right here, 1, 2, 3, 4. It should have been 3, 4. But 3, 4 and 2, 3, we prefer 2, 3. But here, whichever direction you go, it is what? 3, 4. So now the name will be 3, 4. Then you bring the word epoxy. Then the longest chain, which is 6, is what? Hexane. So you have what? 3, 4 epoxy hexane. So that name, which we got, 2,3-diethyl-oxygen, is the same as 3, 4 epoxy hexane. But there are 2 different methods to name them, and any one that you are comfortable with, you use. Then the 2,3 epoxy pentane is also the same as what? the 2-ethyl 3-methyl oxygen. Okay, so they are just two different methods that you have to use in naming epoxy. Yes, wisdom.
Then we like the second one.
Yeah.
It's not about what you like,
Dog.
what you are comfortable with.
The second one is the best.
So we all like the second one.
Dog.
First one didn't hear who's so cry.
Is there a question?
Yeah,
go
dog.
for the second one.
The second name, must you always write them in capital letters?
Oh no. I think my caps was on. That's why it was typing in caps. Sorry.
Okay.
Okay, so that is that on the naming. So, but what I was trying to say is that for those who are saying that you like the second one, yes, if the epoxy is a very simple structure, then you can easily use the oxygen. But as soon as you introduce branches and other thing, then you realize that the second method is the one that can be used. So let me just give you one more structure for you to try your hands on, and then we can then move on. So this one, what do you think will be the name? No, I don't want to use the semi-systematic name. This is the auxiliary type. I don't want us to use that one. Let's use the second method. Please go ahead. If you can name it, just try your hands on it.
3,4-epoxy heptane.
Oh, but there is a methyl group there. Anna.
Yes.
So it will be 3-methyl. 3-methyl.
1, 2, 3, 4. 1, 2, 1, 2, 3.
It's not 3, it's 5.
About 5-methyl, 3, 4. Epoxy.
First discuss you.
1, 2, 3.
So I think it's 3, 4.
3, 4 hepozil.
3, 4.
Hepozi.
It's 7 or 7.
3, 4 epoxy heptane.
3,
4, 5-methyl epoxy heptane.
About 5-methyl. 5-methyl, 3, 4 epoxy 15. 5-methyl, 3, 4 epoxy
3, 4,
15.
3, 4 epoxy 5 methyl heptane.
1, 2, 3, 4.
Metal bay.
That's some cranny.
Metal bay.
Three, 4, 5-methyl epoxy heptane.
It's epoxy, not epoxy.
Hey. Doctor, please, where are you?
Me person you have them.
Let us be serious here.
5-methyl 3,4-epoxyheptane.
That's it. That's it. That's it. Adrian Kade, metal for Kade.
Emily, are you there?
It's 5-methyl 3,4-epoxyheptane.
Guys, it's okay. It's okay. Let's wait for dog.
The answer should be 2-butyl 3-ethyl.
It's okay. It's okay. Let's wait for dog. They're just disturbing.
1, 2, 3. Not. I didn't meet her. We should actually Italo. 1, 2, 3. 1, 2. Hey, meet her. Hey, meet her.
Hey, methyl.
Who said you met me? I'm confused.
Hey, methyl.
2-ethyl
It's a methyl. It's a methyl.
Doc, come and save us. We are lost.
No, come metal no. Yeah.
Battery.
All my sorry is in my head. Because I'm saying I should meet him.
Yeah, no, come metal no.
You see, all my sorry is in my head. Because I'm saying
Definitely is in your head.
Obiano.
5-methyl 3,4-epoxyheptane.
Three, 5 epoxy heptane. 3, 5 epoxy heptane. Three, 5.
Yeah. 5-methyl 3,4-epoxyheptane.
English grammar is for more than one can opposite. Right? I don't know opposite.
4 methyl 5-ethyl. Okay, so it will be 1, 2, 3, 4 methyl 5-ethyl. And so 4 methyl.
Zero. So it can be 4 meter. So 5 meter, 4 meter, opposite, opposite.
Guys, please, dog is not around. I don't think he's here. So let's mute ourselves and wait for him. This is a recorded lecture.
Yeah. Are we through with the naming? Hello.
Yes, sir.
We have
Okay,
tried our best.
what are you getting? Let me know.
5 methyl 3,4
5
epoxy heptane.
5 meter
5 methyl
3
3,4
4
epoxy
3
epoxy
4 epoxy.
epoxy heptane.
Hexane.
Heptane.
Is it hep or hes?
Hep.
Head. Head.
Heptane.
It's 7.
Heptane.
Okay, so the longest chain is 1, 2, 3, 4, 5, 6, 7. So heptane. And then you number from
Heptane,
here
yes, sir.
1, 2, 3, 4. So 3, 4. And then this meter is on the fifth
Yes,
carbon.
sir.
So that is correct. That is correct.
Yes,
So I
sir.
think you people are conversant with this one. So you only take advantage of your strength. Okay. Yes. Okay, so that is that on the naming. Either you use the oxygen or you use the
Hello, sir. Sir,
epoxy method. Yes.
sir. Please,
Yes.
I thought the epoxy heptane will come before the metal since the epoxy is starting with E.
Oh no, the epoxy is a functional group. Oh. So here the metal
Okay.
is a substituent, but then the epoxy is not a substituent. So this is how it is named.
Thank you. Okay, thank you, sir.
Welcome.
5 meter.
Yes, Edward, your hand is up.
Yeah, sir, I beg you. I am asking if it can be possible. The examples that we solved on your board after the lecture, you can save them and give it to us, or you can
Oh,
forward
I
them to us.
see. I think I have been doing that for some other groups, but your group, well, I'll do that. I'll do that.
Okay. Thank you,
All right.
sir.
Welcome.
Harriet.
Yes, Dennis, your hand is up.
Yes, sir. Please, I did for the auxiliary, and I want to Okay, so I see that is correct or not. For the oxygen, I had 5-ethyl propan 3I oxyrate.
Come again.
I had 5-ethyl propan 3I oxyrate.
All right. Yeah, that's fine. Okay, so enough on the naming. Let's move to the synthesis of epoxides. And remember in the semester 1, block 1, when I was teaching you the introduction to organic chemistry, when we got to the reactions of alkenes, one of them was the epoxidation, where an alkene reacts with what? Oxygen to form what? Epoxide. So epoxidation is one of the methods that can be used to prepare or synthesize epoxide. That's epoxidation. So epoxides can be synthesized by the reaction of an alkene with an organic peroxy acid. And the peroxy acids have 3 oxygens. They are different from the carboxylic acids. Carboxylic acids are RCOOH, but then the peroxy acids are RCOOH. We normally call it the per acid. And the process is what? Epoxidation. So this is the structure as you can see on the screen. You have 1 octene, that's an alkene, and that's the structure of what? A peroxy acid. So where the double bond is, the 2 carbons there will form the epoxide. So if the double bond is in the middle, the epoxide functional group will be formed in the middle. Okay, and then always you form carboxylic acid as a byproduct. So epoxidation of alkenes is the oxidation of alkenes with peroxy acids to produce epoxides or oxyrenes. So these are more examples. So if you can see here, an 8-membered ring with a double bond. If you add the peroxy acids, then it forms the epoxides. So wherever the double bond is, the 2 carbons there forms the epoxides. So that is that. These are more examples. You see where the double bond is. This carbon and this carbon. So between them, you form your epoxides. Every other thing remains the same. Here, the double bond is here. So you form your epoxide here. This one, you form it here. So that is the main, reaction that is used to produce epoxides as far as is concerned. We also have this the synthesis from halohydrins. Now, a halohydrin simply means when you have an alcohol functional group adjacent to a halogen. So you have an OH, which is adjacent to a halogen, we call it what? A halohydrin. So when you have halohydrin 2, you can also form an epoxide when there is a base that is introduced to bring about an intramolecular cyclization. So the base will pick on the hydrogen on the alcohol, and then the alcohol will form a ring with the adjacent carbon and then kick off the halogen. So you form your epoxides. So halohydrins can be used to produce epoxides. And how to form halohydrins, you can also use what? Chlorine water, which will give you this, and then you add a base and then you form your peroxide. So that's another method. For the stereochemistry of epoxidation, we say the addition is what? It's syn addition, and it is stereospecific. Okay, so when you use, let's say, trans-2-butene, you will form a mixture of what? 2,3 diameter oxyrene, because the addition of the oxygen to each phase of the alkene generates an enantiomer. For those of you who have done chemistry, stereochemistry, you know what an enantiomer is. Okay, but then when you use the cis-2-butene, on the other hand, you only form the 6,2,3 diameter oxygen. So that is just a little information for you on the stereochemistry. Then the last point is the reaction of epoxides. So when you have an epoxide, you can react it with an acid or a base. So we have acid catalyzed ring opening of epoxides, and anytime epoxides are to react, what it means is that it opens up the ring. Okay, that three-membered ring gets opened up. So when it reacts with an acid, you form a diol, and then the acid that serves as a catalyst is generated. So please take note, when you acid catalyze an epoxide, the acid will first protonate the oxygen, and the protonated epoxide will break off and form a diol, and then acid is generated back. So you always will form a diol. If it is a base catalyzed ring opening, then here you form an OH and then an alkoxy group. Because it's a base, you form an OH and then an alkoxy group. Because you could be using a normal base or even an alcohol to serve as a base. So over there, you will not form a diol, you form what? An alkoxide group and then an OH. Also, with the unsymmetrical epoxide ring opening, that is when you have an epoxide where the ring is what? Unsymmetric, because here there's a metal and here there's no metal. Okay, so if you are adding a base, the base would attack the less substituted carbon. So the two carbons having the oxygen, you see that this one has a metal group, so it is highly substituted. Here it has only two hydrogens, it's less substituted. So the base will go to where the less substituted ring, carbon, and then it will open up the ring, and then you form this product. The reverse is for acid catalyst. If it's an acid catalyst, then the acid catalyst, what is happening is that it is the highly substituted carbon that gets attacked. Okay, it is the highly substituted carbon that the nucleophile will attack. When we were doing with the base, it was the less substituted carbon, but in the acid medium, it is the more substituted carbon that gets attacked. And that one will also open up the ring, and then you form an OH and then a alkoxide group. So look at this and then use that one to appreciate this reaction of epoxides. So if you look at the reagent here, you see we are adding an alcohol in acid. So it is an acid catalyst. But if you look at down here, we are adding an alcohol, but then it's a base catalyst. So in both cases, for the acid catalyst, these two carbons, this one has two hydrogens, this one has what? Two metal groups. So this one is what? Highly substituted. But because we are doing the ring opening in an acid medium, the nucleophile, that's the OCH2CH3, will come to the carbon, which is what? More substituted. The one with the two metal groups. And that's how can we see it here. Then the OH will be formed on the less substituted carbon. But in the basic medium, the base attack will be at the less hindered carbon. So the OCH2CH3 will come here, and then the alcohol will be on this carbon, which is highly substituted. So it's just the reverse. It's just the reverse. Take note of that. This reaction, well, it's not important for us to deal with. So these are some of the reactions in the slide that you can look at later. This is just giving us information about the importance of epoxides in biological processes. When you have time, read them. So that ends the epoxides. So we are done with ethers, we are done with epoxides. And so we are supposed to move to the aldehydes and ketones. Aldehydes and ketones.
Doctor, please, can we go for the break?
Okay. So how many minutes?
Maybe 20.
All right. So let's take about 20 minutes break. When we come back, we will look at the aldehydes and ketones, and then we continue.
Thank you, Doctor.
Hello, Junior. Yeah, yeah. Hello, yeah, yeah. Hello. Hello. Tambourine. Hello, Tambourine. Hello, Tambo. Hello.
We close the lectures or what? It's been a long time where like aldehyde and ketones were on it and nobody is talking to us. So what they go on?
Hello, please, what's happening?
We are on break, please. 20 minutes break.
Oh, all right, senior, thanks. So when are you returning?
I think it will be around 5 minutes time.
Oh, okay, thanks.
Can we continue? I think with Daddy has a ketones, I wouldn't go much. We will continue with that one next meeting, but then we need to start some aspects. Can we? Hey, 33 people. Kindly tell them to come on.
Are we still on break?
Break is over. I'm just waiting for your colleagues so that we continue.
Okay.
All right, so I guess we have to continue. So we started with the alcohol functional group. We've done with the ethers, the epoxides. So another functional group of interest we want to look at is the carbonyl functional group. And the carbonyl functional group constitutes or is made up of the aldehydes and then the ketones. The aldehydes and then the ketones. They are the carbonyl compounds. In terms of structure, the aldehyde functional group, here you have an alkyl group bonded to the carbonyl carbon. So this is the carbonyl functional group, which is made up of the carbonyl carbon and then the carbonyl oxygen, and then a hydrogen. But in the case of the ketone, you have two alkyl groups bonded to the carbonyl carbon and then without any hydrogen. So it means that the ketones have two R groups, the aldehydes has one alkyl group and then a hydrogen. So that is their structural differences. These are some examples of aldehydes and ketones. And we have the acetophenone, which is a ketone. We have acetone, which is a ketone. We have ethanol, which is an aldehyde, and benzaldehyde, which is an aldehyde. These are very common examples of them. We also have some important aldehydes and ketones, which we know of them. The benzaldehyde, those of you who have ever taken Indian almond, have you taken Indian almond before? Are you there?
Yes, sir. Indian what?
Do you know Indian almond?
Hey.
Patience. Do you know Abrofunkati? Do you know Abrofunkati?
Yes.
Yes, sir.
You know Abrofunkati?
Indian almond. I thought you said Indian hemp.
Not Indian hemp. Oh, hey, please. Indian hemp say. Anyway, very soon I'll ask that one too. Maybe some of you have taken Indian hemp. But Indian hemp is medicine, so and they are alkaloids, they are all medicine. Yes, so when you plug the fruits and then the hard nut, when you crack it open, you see that whitish substance in there. It contains a lot of what? Benzaldehyde, which is an aldehyde. Then the lovers of ice cream. Those of you who like ice cream, there's one flavor that is very sweet, the vanilla ice cream. And the vanilla ice cream contains an aldehyde called the vanillin or the vanilla beans. Then also this particular plant, which is very, very medicinal, the cinnamon powder or the cinnamon tree, which it has a number of medicinal properties, also contains a particular aldehyde called cinnamaldehyde. And this cinnamaldehyde is said to be contributing to most of the health benefits that cinnamon powder or cinnamon provides. Then I'm sure we all know camphor. You all know camphor.
Yes, naphthalene.
Now, is that naphthalene?
So with this one,
Is
with
it
this
not the
one,
same thing?
is there a
They are not the
difference between
same.
camphor and naphthalene?
Okay.
There is a difference between naphthalene and
Camphor.
camphor. Camphor is what you can see the structure there. You see that there's a double bond oxygen there, a ketone.
Yeah.
But naphthalene is a hydrocarbon, aromatic hydrocarbon. When we're dealing with introduction to organic chemistry and we go to aromatics, we say we have what? Aromatic hydrocarbons, the common one being benzene. Then we have naphthalene, when two benzene fuse together. That is naphthalene. Then we have anthracene, when three benzene fuse together in a straight chain. Then we have phenanthrene. Okay, all these things are aromatic hydrocarbons. So there's a difference. Now, camphor, even now, is seen as is carcinogenic. So its usage has been restricted now. I don't know whether people still use it, but I mean, growing up with my grandmom, what I know is that she would fetch water, those days river water, and put it in a pot, and then she will put camphor inside and cover it.
Yes.
And so in the village, when you open it and you just take even a half full of a cup and you drink it, it's more than the one in the fridge that is being enjoyed by those in the cities, but now camphor is being started to have some kind of anti-cancer, or it's carcinogenic in a way.
Yes.
So its usage has been restricted or banned now. These are all aldehydes and ketones. And before even I go on, the other examples, so that you know that they are very common things that we always deal with. The glucose that we always take, the sugar, it is an aldehyde. Okay, those doing the natural product chemistry, I'm sure we have done classification of carbohydrates where we have monosaccharides. An example is glucose. So glucose is an aldehyde. Fructose is also another sugar, and that is also what? A ketone. Okay, so aldehydes and ketones are very common in our everyday life, and that is why it is important we learn something about them. How do we name them? How do we name them?
Hello, sir.
Yes.
Please, before we go to the naming, I want to ask this question. When you made mention of the camphor and then the naphthalene balls, those ones are common. We come across them always in our life. One, how do we even those on the market now? How do you differentiate? How do you know that this one is camphor and then this one is naphthalene ball? We have been using some in our bathrooms and other stuff, and also in steam inhalation. At times, some homes they do
steam
it.
inhalation.
Yeah, steam inhalation. At times,
Okay, so
they just crash it or put it.
Okay, so specifically, let me say that most of these carbonyl compounds have some kind of scented properties. Okay, and some of them the other compounds that also behave similarly in terms of their physical property. So if you go to the market, there are other things that look like white scented, but they might not be naphthalene balls. They might not be camphor. Okay, they could also be something different. So in terms of the question you asked, and as a chemist, you know, you cannot just sometimes look at a thing in the physical appearance and sometimes conclude, unless it is well labeled and then is being satisfied by the FDA and is being sold. But if it's not well labeled and satisfied by FDA and being sold, then you have to bring it to the lab and perform some tests. Do you understand? Some basic tests that will confirm that, oh, this one is camphor, this one is naphthalene ball, this one is this one is that. Okay. As for the things that we find in our marketplaces, I tell you, most of them are just killing us because apparently due to the high level of what food adulteration and then food contamination, somebody will go and buy palm oil. You know palm oil that we eat.
Yes.
And because there's a high demand for palm oil, the person will dilute it with some other things, water and then other things. Okay. Now, when they dilute the original palm oil, it loses its what? Texture and color. Do you understand? So maybe they will go and buy 2 gallons of what? Or 2 gallons of palm oil, original one. And because there's a high demand for it, and the person wants more profit, they will dilute the 2 gallons to maybe about 10 gallons by adding water and other things. Now, when you do that, it affects the texture and then the color of the palm oil, the original one. And for them to get the color back, they will add Sudan dye, which is a carcinogenic reagent. And here we have Sudan dye 1, 2, 3, 4. And this class of Sudan dyes we are talking about, when you add them to the palm oil that has lost its color and texture, it will restore it. It will make it look reddish. Okay, so that when you take it to the market, people know that, oh, this is really palm oil. And then they'll be eating it. Meanwhile, they'll be eating what? Chemicals. Okay, they'll be eating Sudan dyes. Today, the rice, the milk, the honey, and most food substances, okay, even this, how do you call it? Those, the ladies who prepare stew, how do you call them? Is it
spices?
The spices. Good. Thank you, patient. The spices, which more or less were meant, okay, to enhance the nutritional value of the stew. Today, because of the high demand for most of them, they miss other things so that it becomes a lot. And again, they miss other things so that those spices can stay for long. And so the spices that you think you are preparing stew to eat, you are rather eating something else. And we are dying. Yes, we are dying slowly. People are getting sick. Sometimes you'll be there and say, somebody says, oh, but she wasn't sick. Oh, he wasn't sick. Oh, we are all sick. In fact, we are all sick. As we move up and down, we are all sick. And we are all walking like dead beans. Because even where you say that, oh, me, I want to be careful with the food I eat. I want to prepare my own food. The things that you are going to buy to prepare your own food is contaminated. It's adulterated. And for those of us, the bachelors, the guys who don't want to cook, and they're always buying from the outside, the roadside. As for them, the contamination is about 100 folds.
Too much.
Yes, they go and then they drink the soup like as if their head it's all poison that we are eating. So in fact, we are all sick as we move. That's why. Yes. So food contamination and then adulteration is a worry situation now in this part of our world. Well, so I only want to let you know that aldehydes and ketones, these carbonyls, they are very, very important, and that's why we need to know something about them. So how to name them? The common ones or the simple ones have some common names, which though they are common names, but they are accepted everywhere. One of them is formaldehyde. That's the first member of the aldehyde. That one has only one carbon. Okay, formaldehyde. And formaldehyde has a trade name called formalin. And I'm sure we have all heard of formalin. If you go into the biology lab, they use formalin to preserve insects, preserve specimen, okay, so that they don't go bad. Those days, formalin used to be one of the key chemical that is used to preserve even dead bodies. So these are aldehydes, acetaldehyde, benzaldehyde. When you say benzaldehyde, though it's a common name, it's accepted. The same way, if you consider the ketones too, the same thing. In terms of the nomenclature, that's the IPAC system. What we normally do is that, yes.
Please, I just want to chip in something, though it's not part of what you're doing. Because you mentioned the formaldehyde,
yes.
I want to say that now people are using it to bake bread. And so when you buy bread, when you buy bread, you keep it for about a week and then it won't spoil, it won't do anything. Unlike before,
so you
when
see,
you buy bread after some few days, you see that
yes, of course,
it will start
the natural, yes, Mercy. So the natural thing is that sometimes when you go and buy bread into the house, you want to finish it within a day or two. If not, it will go bad. Do you understand? But you see, now these people have found a way to preserve the shelf life. But the question is, what are we doing in the preservation of the shelf life? If we were to be doing something right, there's no problem. But you using formaldehyde in the preservation, you just go and read about that chemical and what it can do. So the bread that we are eating, every morning they say take breakfast. And then you get about 5 or me, I don't even slide my bread. I cut it big, so that I'll be dropping it in the tea. You know, so imagine what is going into my system. Imagine what will be going to my system. So I mean, personally, but that wasn't because of what our lady just said. I'm even hearing it for the first time. But for about 2 months now, I have decided to go without bread. I'm doing something, and I'm just trying to stay away from bread. And there's some other things. Is it?
will increase in size when he eats more bread.
Yes. So I'm trying to manage something. So, but I think it's a concern for us all. We are all learning chemistry. We are all
It
learning
is
this.
also used on some fresh fish, like the tilapia and other ones.
Yeah.
The one they put on table and they
So
sell it.
you see, if the Food Drugs and Authority, the FDA, were to be having
Those people
more,
are not doing their work.
if they were to be having more human resource, like they have a lot of people at the job place, and then they have to throw them onto the market, and then they have the equipment to test for most of this food, then a lot of people must be arrested. And when they are arrested, they should be jailed. But then in Ghana here, go and then pick somebody. If you go and pick the market woman who is adulterating food and is selling to us and is killing us, then they will do politics with it. They will say that why is the government trying to take their livelihood from them? They won't vote for them. You know, meanwhile they are killing human beings, but they want government to allow them to continue to kill human beings because they think that their livelihood is on the line. So we have become greed. We have become greed as a people. Everybody want to outsmart the other, and we end up killing ourselves. Today, if you go into the hospitals, young babies are born, and then all kind of health issues because the mother herself was pregnant, was exposed to a lot of this kind of challenges. But then, as scientists, we need to go ahead and research and make sure that we get things done appropriately going forward. If not, all of us will die, and this planet will be there without anybody. If we don't stop this kind of things. All right. So for the IUPAC name, what you need to do is simple. You have to identify the functional group. Like on the screen, they are all having the aldehyde functional group. Then check how many carbons are in the chain. Usually, aldehyde functional group are always at the terminal end. They are always at the terminal end. So if it is a 1 carbon aldehyde, like this one, which we said is for formaldehyde, then you consider the corresponding alkane name. How do we call a 1 carbon alkane? It's methane, isn't it? A 1 carbon alkane is methane. A 2 carbon alkane is what? Ethane. A 3 carbon alkane is what? Propane. So the corresponding alkane name, the last letter E, you omit it and then you add the word, or you add the letters Al. So methane becomes what? Methanol. Because it's a 1 carbon what? Aldehyde. This second one is a 2 carbon aldehyde. So from the corresponding alkane name of a 2 carbon ethane, you omit the last letter E and you replace it with what? Al, and becomes what? Ethanol. This one is a 4 carbon. 1, 2, 3, 4. So from butane, you omit the last letter E and then you add Al. They becomes what? Butanol. So that is how aldehydes are named. Of course, in the case of the aldehyde, because they are always at the terminal end, there's no need to even number the chain and then indicate the position, because it will always be 1. It will always be 1, position 1, because they are always at the terminal end. So it just butanol, you don't say 1 butanol. It just ethanol, you don't say 1 ethanol. It just pentanol, you don't say 1 pentanol. It is only when there are other functional groups or other substituents which will require that maybe the position be indicated. That's when you do that. So here it's an aldehyde. And so if you pick the longest chain, 1, 2, 3, 4, then it means that this one is a substituent. This methyl group is a substituent. Then again, this methyl group down here is also what? A substituent. So in this case, because there are 2 substituents, you need to number the position, the longest chain containing the aldehyde. So you start from here so that you give the least number to the aldehyde. So 1, 2, 3, 4. And the 4 carbon chain is what? Butanol. Then you bring the substituent name before the parent name. And the 2 methyl groups are on position 2 and 3. So 2, 3 dimethyl butanol. And that becomes the IUPAC name for the aldehyde compound. Then the ketones.
Sir,
Yes.
Sir, please back more, the previous slide now. The previous slide.
Okay.
When you counter the longest carbon chain, where the O double bond and then the H, that place there's a carbon, right?
Yes, that is the carbonyl carbon. Okay. You see, I show you the functional group. The aldehyde functional group, there's a C here, double bond oxygen. But you see, this one is a dot line method. So the dot line method, I will not type the C there, but you know that there is a carbon there, which is double bond oxygen, double bond bonded towards oxygen. So yes, there's a carbon there. All right. So now let's move to the, as for this one, we will not use the chem draw. At least it's simple. The naming of aldehyde is simple. So you can get more examples yourself. All right. So now with the ketones too, here the ketone functional group can never be at the end of the chain. It is always in the middle of the chain. So if you take this one, you could see that if you take this carbon, 1, 2, 3, the ketone functional group is in the middle of the chain. 1, 2, 3, 4. Okay, this one like this, 1, 2, 3, 4, 5, 6. So for the ketone, you should always number the chain and indicate the position of the ketone functional group. Now for the first one, we didn't bring any position because there's only one way that you can locate the ketone functional group. So it is 1, and then this one will be 2, and then this one will be 3. If you count from here, it will still be 2. So it becomes straightforward. You don't need to bring the position. But then the length of the chain, you also consider the corresponding alkane name. This one is 3 carbons, and it's propane. So the propane, in the case of an aldehyde, you omit the last letter E and add Al. They become propanol. But in the case of a ketone, you omit the last letter E and then you add O-N-E. 1. The spelling of 1, O-N-E. So it becomes what? Propanone. All right. Now, if you go to the second one, where the longest chain is 1, 2, 3, 4, that is butanone from butane. You omit the last letter E and you add O-N-E. So butanone. But then here we say it is 2-butanone because you need to number the chain. 1, 2, 3, 4. It becomes 2. If you number from here, 1, 2, 3, it becomes 3. But then the numbering should be such that the functional group is given the least number. So you move from here, 1, 2, 3, 4. So butanone. The other names down there are the common names. Okay. So that one, you consider this and this as a substituent. So you have what? Ethyl methyl ketone. If there are 2 methyl groups, dimethyl ketone. And then you go ahead. Over here, you can see that the longest chain will be 1, 2, 3, 4, 5, 6. And you have to number that chain because the ketone functional group can be positioned at different places aside where it is now. You can bring it here. You can also bring it here. And in both cases, you have a different name. So it means you have to number. Now, if you number from here, the ketone will be 3. If you number from here, to be 4. So you prefer a 3. So 1, 2, 3, 4, 5, 6. So the methyl substituent here becomes 5. Methyl 3 hexanone, because a 6-carbon alkane is hexane. And you omit the last letter E and add O-N-E. Then it becomes what? Hexanone. Hexanone. So that is the naming. Now let's look at the physical properties. We will be ending with this one. Next week, I will continue with the aldehydes and ketones, whereby I will take the synthesis and then the reactions. Then we will move straight to the carboxylic acids. So, so let me finish with the physical properties of aldehydes and ketones. Yes.
Yeah, so if I heard you well, the clear difference between the ketones and then the aldehyde with respect to the nomenclature is with respect to the position of the functional group, where the aldehyde is the terminal and then this one is in the middle.
Yes, and that for the aldehyde, when you count the longest chain, the corresponding alkane name, you omit the last letter E and you add Al. So ethanol, propanol, pentanol, hexanol, octanol, and so on and so forth. If they are substituents, they are named before the parent name. But then, if they are substituent and you are doing the counting or you are numbering, always start from the aldehyde functional group. For the ketone, after selecting the longest chain, the corresponding alkane name, you omit the last letter E and you add ONE. So if it is 3 carbon propanone, 4 butanone, 8 octanone, 9 nonanone, and so on and so forth. But then, because the ketone functional group is always in the middle of a chain, after numbering the chain by way of giving it the least number, you should indicate the position of the ketone functional group in front of the parent name. And if they are substituent groups, they can also be named before the parent name. Now, aldehydes and ketones, physical properties. The carbonyl functional group is polarized, okay? That is the carbon double bond oxygen is polarized because oxygen is highly electronegative, so it draws electrons to itself more, and so doing, it becomes partially negative, and the carbonyl carbon become partially positive. So the carbonyl functional group, that is the C double bond O, that bond is polarized. The carbonyl carbon become partially positive, and then the carbonyl oxygen become partially negative. So for that reason, we say the aldehydes and ketones are what? Polar. Okay, they are polar. But then their polarity is not compared to, or it's not close to that of the alcohols. Because for the alcohols, the oxygen-hydrogen bond is highly polarized. And so compared to the oxygen-carbon bond, so alcohols are more polar than what? Aldehydes and ketones. Again, aldehydes and ketones do not form hydrogen bonds to each other. They only form hydrogen bonds with water. Okay. For that reason, if you are to compare the melting point and the boiling point of alcohols to aldehydes and ketones, the alcohols will have a higher boiling point than the aldehydes and ketones. They will have a higher boiling point than the aldehydes and ketones because in alcohols, there is what? Hydrogen bonding that the alcohols form with water and then they also form with themselves. So an alcohol will form a hydrogen bond with itself and it will form a hydrogen bond with water. So that makes the degree of hydrogen bonding very much pronounced. And that's why they have the corresponding high boiling point, being determined. In the case of the aldehydes and ketones, they can only form hydrogen bond with water, but not with themselves. So aldehydes and ketones have lower boiling points when we compare to alcohols of similar size. Again, aldehydes and ketones are soluble in organic solvents, and those with fewer carbons are also soluble in water. Because of their moderate polarity, water is a polar solvent, so it will develop polar compounds. Because aldehydes and ketones are moderately polar, especially the fewer carbons, carbon 1, carbon 2, carbon 3, those ones are soluble in water. But then as you increase the carbon chain, solubility in water decreases. But then all of them will dissolve in organic solvents. And also the type of hybridization in aldehydes and ketone is the sp2 hybridize. Is the sp2 hybridize. So we will end, and like I said, or we should continue.
No, Doctor.
Let's move.
Please, sir, we should end.
We'll rest.
Read over.
Yes, I
Please,
don't want to bombard
have
you
it.
with so many. At least we've done
We are tired,
ethers
sir.
today. We've done epoxides, and we have started with the aldehydes and ketones after their naming, and then their physical properties. So you can digest on this one. Next week, we will deal with the synthesis, how to prepare aldehydes and ketones, and then their reactions. Then we can move to the carboxylic acids. Yes.
Sir,
Yes.
please
Lydia.
send the recording to us on time so that we can go over what we've done today. I'm pleading.
Madam Lydia, the recording is being done by Code. Okay, so the e-learning unit. And I think you are in touch with them. So the course rep can always demand for the recordings and then they will release it. I don't have a direct access to it. Yes, please.
All right, thank you.
Good.
Doc,
Yes.
you out of the melting, did you have anything about melting? You didn't talk about melting point. I don't know whether aldehyde and ketose.
Yeah. So when we talk about physical properties, we can talk about boiling and melting point. Okay. What we are saying that there are some aldehydes and ketones that exist as solid. If they are solid, we determine melting point. If they are liquids, we determine boiling point. But then the explanation is that if you compare aldehyde and ketone, whether it's boiling point or melting point to an alcohol, they will have lower boiling point and melting point because they do not form hydrogen bonding with themselves. They rather form with water. And so they don't have much of hydrogen bonding in them, which will require more energy to break. Okay, so whether it is melting point or boiling point, it depends on the state of the compound, whether it is solid or it is liquid. If there is no other question, then
hello,
thank
Doc.
you.
Hello, Doc.
Yes. Yes.
Please, the tutorial questions.
Yes. So the course reps, please keep me updated. And you see, from now to the next lecture, if you don't get onto me and then you wait, we will meet next week and then we'll be talking about the same thing. But then I will have to I have a number of questions, tutorials, review questions that will also serve as a guide in your preparation. Sometimes it helps you to also understand how questions will be asked and what have you. So yes, they should reach out to me. Are we on the same platform so that I can share them also myself? If not,
The chemistry major page.
Okay. Yes, I'm there. All
You're
right.
on the online center page. You are there, so you can put it there.
All right. That's fine.
Okay, it's not all of us that are on that page. So in case
Yeah.
not
Festus, you
all
can
of us
also
that
pick
are
it.
there.
Festus, you can also pick it up from me direct.
Yeah, I'll contact.
Yes, and then
Okay.
we share with your biology people.
I beg when it comes, share it with the physics major as well. Thank you.
All right. Thank you for coming
First,
and have a
when you get
blessed
it,
evening.
share it on the chemistry and all the platforms.
Bye for now.
Festus.
Thank you very much,
Thank
sir.
you, sir. Festus.
Bye-bye.
Hey, Festus.
Yeah, senior.
Complain of
Yeah, when you get it, share it
formalin
on the
phase or
chemistry
phosphate
platform as well.
Please,
The
I
rep,
don't belong to chemistry platform.
you can
Okay,
share it on
no
the rep.
problem, no problem.
The reps platform. The reps.
Okay.
The rep platform too. Okay, thank you.
You're welcome, sir.
That's me.
Have they closed?
Ebe. Ebe. Ebe.